Hi folks, this is Nat, and this is going to be your video lesson on identifying polygons by their number of angles and sides. The very first thing we're going to talk about is the idea of what is a polygon. And the short answer is really that anything that you probably think of as being a shape that has straight sides is going to be a polygon. The more mathy definition is that a polygon is a closed plane figure formed by three or more line segments, and we'll kind of look at what that means. Let's start with this idea of being closed. When a polygon is closed, it means it can't have like any stray ends. Every line segment's endpoints have to join to another line segment's endpoints. So for example, this could never be a polygon because it's got these kind of loose stray ends. Similarly, this could not be a polygon because it's got this stray end kind of right here, even if we imagine that this is closed over here. Circles can't be polygons. We'll talk about why in a second, but actually one more example of a non-closed plane figure. So here is one more example. Now you could think of this as two individual triangles that just happen to be sharing a single point. But if you were trying to think of this as a quadrilateral, it wouldn't work because you've got these line segments intersecting one another, not at the end point, which can't happen in a closed plane figure like a polygon. When we talk about a plane figure, that means it exists on a single plane. So whenever we talk about polygons, we're talking about two-dimensional objects. They can't exit the second dimension. As soon as they become three-dimensional, they are no longer polygons. So all the line segments would have to fall on the same plane. Finally, a polygon has to be made up of line segments, which means things like, I don't know, a circle are not going to be polygons. Anything with any sort of curve or arc to it is not a polygon. It has to be exclusively made up of straight lines. Even if most of it's made of straight lines, but some other chunk of it is not, that is not going to be a polygon. It can only be made from line segments. Generally, it's not super hard to name polygons. That's going to be what we're going to focus most of our time here on. They're just named by the number of sides and angles that they have. And we've actually talked about certain polygons already in our geometry unit. As you might remember, a polygon that has 3 sides, that's the minimum, is going to be a triangle. Hopefully that's not a big surprise. And one that has 4 sides and 4 angles is going to be a quadrilateral. And these are the ones that we've covered already. From there, we just keep adding sides. 5 sides and angles is going to be a pentagon. 6 sides and angles makes a hexagon. 7 sides and angles, regardless of how they look, makes a heptagon. As you can see, we've got 7 sides and angles there. Even if they're concave, still a heptagon. 8 sides and angles makes an octagon. You are familiar, I'm sure, with octagons. You get up to 9 sides and angles. You have what's called a nonagon, N-O-N-A-G-O-N, nonagon. And then finally, for us at least, 10 sides and angles makes a decagon. And these are going to be the ones that you're responsible for knowing. Everything from 3 sides to 10 sides. So just a quick review. We have triangles, quadrilaterals, pentagons, hexagons, heptagons, octagons, nonagons, and decagons. We also previously talked about the idea of concave versus convex, but we're going to review it again here really quickly. These are the two ways of classifying certain types of polygons. When one is concave, it has a reflex angle or has that sort of pushed-in section. Convex does not have that. So looking at the 2 angles we have here, we can see that our decagon has this really large reflex angle on its interior. That's going to make it concave. It has a couple reflex angles, as a matter of fact. Here's another one. There's another one. Our nonagon also has some reflex angles going on. Looks like this might be bigger than 180. This is certainly bigger than 180. So it's also going to be concave. On the other hand, our octagon has absolutely no reflex angles. There's nothing I can find here that is going to be bigger than 180 on the inside. So it's going to be convex. Our heptagon has that pushed in angle here. So that seven-sided shape is also concave. Our hexagon is convex. It does not have a single reflex angle in it. No pushed in part at all. Similarly, all of these, the triangle, quadrilateral, and pentagon, are all convex, no reflex angles. Interestingly, the triangle, it is impossible to have a concave triangle. You might try that out if you're interested. The other vocabulary word we want to talk about today is the idea of regular. Regular in everyday speech is just like saying normal or average or something like that, but it has a very specific meaning in math where geometry is concerned. A regular polygon is a polygon where all the sides and angles are congruent. So basically all the sides, all the line segments would have to be the exact same length, and all the angles connecting line segments would have to be the same. Here are some examples of regular polygons that I made using GeoGebra. If you look at this top one, I can count the sides and say, oh, that's 1, 2, 3, 4 sides. That makes that a quadrilateral, and it's a regular quadrilateral. Now, it's kind of worth noting that we don't typically call that a regular quadrilateral. We have another name for it. So a square is just a regular quadrilateral. If I look over here, I've got one that has 1, 2, 3, 4, 5, 6 equal sides, all equal angles. That's a hexagon, so it's a regular hexagon. And if I look down here, I've got 1, 2, 3, 4, 5, 6, 7 sides. That makes that a regular heptagon. And this last one has 9 sides, which makes this a regular nonagon. So again, regular in a geometric sense just means that all the sides and angles are equal, and it ends up being this progressively rounder and rounder looking shape. The more sides that you have, kind of an interesting note is that from a geometric perspective, a circle is actually just a regular polygon with infinite numbers of sides. The last thing we're going to cover today is the different number of degrees in the various polygons, so what the angles have to add up to. And again, you already know some of these. So if we talk about a triangle has to always add up to 180 degrees. And we talked last time about a quadrilateral. A quadrilateral has to add up to 360 degrees. And every other polygon of any different number of sides has a specific number of degree measurements in it. And rather than memorize all of these, the better thing is to actually understand where this idea comes from so that you can easily calculate how many should you encounter one you've never seen or you forget something. Basically, the number of degrees in a polygon comes from the number of triangles that fit inside of it. So our starting point is always going to be this idea of a triangle has 180 degrees. If I come up and look at my quadrilateral, I can divide that from a single point into exactly 2 triangles, each of which would have 180 degrees inside of it, making a grand total of 360 degrees, the measurement of a quadrilateral. Similarly, let's look at our pentagon up here. If I start dividing up a pentagon from a single point, you're going to notice I can make 2 lines that don't already exist to the other points or the other corners. I could make these over here, but they already exist as the line segments or the sides of the polygon. So I don't need to do that. Each of those triangles inside is exactly 180 degrees, meaning a pentagon has 3 180-degree triangles in it, and 180 times 3 is going to be 540 degrees. And that's how many degrees are inside any pentagon. Moving on down, here's a hexagon. I can make my connections. And I'm going to see 1, 2, 3, 4 triangles, giving me a grand total of 720 degrees in any hexagon. These are all regular, but this would be true no matter which sort of thing that I made. Now, if you're really on it, you may have noticed a pattern already, which is that the number of triangles that fit inside of a polygon seems to be 2 less than the number of sides. So a triangle with 3 sides has 1 triangle inside of it. That's 2 less than 3. A quadrilateral with 4 sides has 2 triangles inside of it. That's 2 less than 4. A pentagon with 5 sides has 3 triangles inside of it. And a hexagon with 6 sides has 4 triangles inside of it. So we can save ourselves some trouble if we kind of get this pattern down. And if I say I know that this is a nonagon, because I've counted the sides, it must have 7 triangles inside of it. And if each of those 7 triangles has 180 degrees, that means that a nonagon is going to have a total of 1,260 degrees inside of it. And this is a pattern that'll hold up no matter how many sides I get to. If I have a 20-sided polygon, I can figure out how many degrees are going to be inside of it. I could also do things like tell you how many degrees each angle would need to be, say, in a regular one of these polygons. For example, you've already seen that in a regular triangle, each of the degree measurements gets divided up, or the 180 degrees gets divided up evenly among the 3 angles there, so that each is 60 degrees. And it works the same way in any regular polygon. You've seen in a square, a 360-degree quadrilateral, that they each get divided up evenly into 4 90 degrees. And that's just 360 divided by 4. I could do the same thing with my pentagon. I've got 540 degrees in a pentagon, and I've got 1, 2, 3, 4, 5 angles. So if I divide that 540 degrees up evenly among my 5 angles, I know that each of those angles in the regular pentagon is going to have to be 108 degrees. And then once again, this holds true for any polygon I would like to calculate that for. So I can always find the number of degrees for a regular polygon. And here are your practice problems. Make sure that for numbers 1, 2, and 3, you both tell me what sort of polygon it is by number of sides, and also tell whether it's convex or concave. Number 4, you need to just tell me how many degrees are inside of a decagon. What would they sum to? Good luck.